All right, recording, rolling. It is Monday, October 22nd. Today I'll take you guys through lesson 4.4, which is dividing polynomials. So like polynomial fractions. That's where we left off last time on 4.3 was, well, operation. So it was adding, subtracting, and multiplying. But the dividing, there's some, well, fun methods. Now, some of these are pretty straightforward. You can, like if you have a monomial, you can just divide each term. So that's not too bad. There's also long division. I'll show you guys some examples with long division. And there's also something called synthetic division. So I'll show you each one of those. And then if you want to see more examples, of course, I have uploaded like an hour of examples for those. I opened up Alex 4.4 and 4.5 for you guys. And then, 4.5 is a bit involved, but we'll do that one tomorrow. But I'll get you guys ready for this Module 4 quiz, which is going to be on Friday. All right, so you guys good so far? Good so far? All right, Module 3, here's my top mathematicians. So awesome job if you made top mathematician. Yeah, so overall, you guys doing better and better here. All right, so 4.4, dividing polynomials. All right, so if you are dividing polynomials here, so you guys know you can have a numerator divided by a denominator, and then that'll be the fraction. Right, so I might use these terms in here, dividend and divisor and quotient. Right, so that refers to those also. So you can see that right there. All right. So let's try here. I'll start with one where I'm just basically dividing by a monomial. So here, I'll pick this. Yeah, this one right here. So what if I have 6x squared minus 15x? This is all divided by just very simple monomial. Great. Guys, mono, that means one, right? So monomial is just one term. There's only one term in the denominator. Okay, so what's that? Guys, if you just have a single term in the denominator, are you allowed to split this up into different fractions? Yeah, you totally do that. So this is the same thing as 6x squared divided by 3x minus 15x over 3x. Isn't that the exact same thing? Okay. Great. So, guys, what if it's the other way around? What if I have two terms in the denominator? Are you allowed to split up the denominator like that? No, just the numerator. Okay. Here, let me give you guys a counterexample. So if you see a plus b all divided by c, you can totally say, oh, that's the same thing as a over c plus b over c. That's okay. Okay. But what if you saw something like d divided by e plus f? Are you allowed to say, oh, that looks like d over e plus d over f? Is that a thing? No. The simplest you can have it is as I gave it to you right here. So this is not valid. Okay. But this can be. Okay, so you guys know that. And that's all I did right here. Right? We just have one monomial, so I just split this up into two fractions. Okay. Now, can I simplify here? Guys, what's 6 divided by 3? 2. And what's x squared divided by x? Yeah, x. Because that's the same thing. X times x divided by x. 1 to x cancels each with the other one. Then how about over here? What does this come out to? This term? 5. Yeah. And the x's just cancel. Okay. So I think that's just that right there. 2x minus 5. Okay, which is exactly what the book's showing to. If you graph this, suppose I plug this expression into Desmos, would it just show a straight line with the slope of 2 and the y-intercept at -5? Right? Because on the main video where I do an hour of examples, I graphed a lot of these on Desmos, so you can see exactly what the graph looks like too. And I've actually one key up for you guys on that for here today. Okay, are you guys okay with that? Okay. Let's do an example with long division. I'll take you exactly through one of their examples here, and I'll do another example later. So you get a couple of examples of long division here in class. So long division. I'll remind you guys what long division is. Do you guys remember? How about this, guys? What is 7 times 12? 84. Yeah, 7 times 12, 84. Right. Therefore, guys, what is 84 divided by 7? What is that? It would have to be 12, right? Okay. Now, how can you show that with long division? So long division goes like this. If I have 84 divided by 7, that's 84. And then you put this division sign, and you put the 7 out here. So here's the dividend, here's the divisor. This is familiar, maybe from the past. You guys have done long division before, right? Okay. Right, so I'm going to go digit by digit, starting with the big digit. So, guys, how many times does 7 go into 8? Once. So I put 1 on the top. Then I multiply it here. So, okay, so what's 1 times 7 is 7. And then, guys, what's the next step? Subtract. 8 minus 7 is 1. And then I bring down the 4, 14. All right, so how many times does 7 go into 14? 2. And then that 2 times 7 is 14. Subtract, you get 0. Once you get 0, then the process finishes. And here's the answer right here. Aha, exactly what you knew it was going to be. It's 12. Okay. Now, can you do that with polynomials? You guys ready to do some polynomial long division? Okay, here we go. So take this example. Let's do x squared minus 5x minus 36. That's all divided by x plus 4. Okay. Oh, by the way, you might see that you can actually factor. Right? Okay, let me do factoring first to show you that you can do this. Guys, can you factor the top as x minus 9, x plus 4? Is that because let me FOIL this? X squared minus 9x plus 4x is negative 5x. Negative 9 plus 4 is negative 36. X plus, okay. Right, do you guys see that? And then, guys, does this cancel? So, what is the answer to this going to be? X minus 9, right? You guys see it? Okay. So, let's check. I wonder if the long division also gives me the exact same answer. This little thought cloud right here. So, let's take the x squared minus 5x minus 36 and put this division right here and divide it by x plus 4. Okay, you guys see I can do this? Let's try it out. I wonder if I'm still going to get x minus 9 out of this, because I better, because that's the answer. Okay. So x plus 4, well, that's sort of 2 terms, so maybe I'll go 2 terms out here. Or actually, you know what? Even simpler than that. You can just really just focus on the first term of each. Okay, so how many times does x go into x squared? How about x times, right? X times? Right. It would be 2 if this was a 2x, then I would say 2. But if it's x squared, I'm going to say x times. Right? Then what I'll do is I'm going to take this x and I'm going to multiply it by this whole binomial term here. So guys, what's x times x? X squared? And what's x times 4? 4x. So that would be like that, right? Okay. Now remember the long division we just did. Didn't we subtract that from the original statement? Okay. So I'm going to subtract all this. Okay, you guys get that? Okay. Now, a lot of times what I'll do, especially if I have a bunch of negatives flying around, is I'll go ahead and distribute this negative and then just add it. So can I do this? Can I say plus, minus, minus? Can I just do that? Right? Now, what's x squared minus x squared? 0, which we set it up to be that way anyway. That's why I have the x up here, because that would happen. And then what's negative 5x plus negative 4x? Negative 9x. Okay? And then can you take this negative 36 and bring that down? So minus 36. Okay. Guys, how many times does x go into negative 9x? Negative 9 times. Okay. And then take this and multiply it. So negative 9 times x is negative 9x. Negative 9 times 4 is negative 36. Oh, look at there. So, bing. You get 0, we're done. And is that the answer right there? X minus 9? Yeah, which when we did the factoring approach, that's also what we got. So we just did 2 different methods right there on the same screen. Got the exact same answer. Yeah.
But what if the 9 and the x both cancel out? Not the, like, do you have a negative 9 and then plus the 9x?
Wait, what's wrong?
At the bottom, like.
Right here?
No, at the bottom.
Right here?
Yeah.
Yeah.
Why doesn't the x also?
Oh, it does. It's all 0. Yeah. So that's supposed to cancel too. Yeah, so that's 0. That's 0. So the whole thing's just 0. Yeah. Okay. Right. Yeah, good. It's good. Okay. All right. Are you ready for something a little bit weird? So I'm going to show you guys something called synthetic division. Right? You guys ready for this? Synthetic division. All right. So I'm going to spell this out. Synthetic division. Actually, I'm going to do 2 examples with you guys with this, because your book has 2 slightly different types of examples. Okay? All right, so here's what we're trying to do. We're trying to take 3x to the 3 minus 2x squared minus 53x minus 60, okay, and divide that by x plus 3. Okay. Now, could you, if you want to, could you use long division and get the right answer? Yeah, you could do that. We just did long division. You could totally do long division. Okay? But there's sort of like a shortcut method that sometimes this is actually way faster. Right? What I'm going to do is I'm just going to take the coefficients on each of these terms. So that looks like a 3, that's a negative 2, that's a negative 53, and that's a negative 60 for a constant. Okay, and just list this out. Notice I haven't even written anything about x. I just throw out the coefficients. Okay. Oh, by the way, guys, if there is a like if you skip over power of x, like I had x to the power of 4, and jump straight to x to the power 2, and I skip over x to the power 3. Okay. then wouldn't I have to write in a 0 right here to take the place of x to the 3? Okay. So if this was x to the 4, I would still have this as 3 for this coefficient, but I have to have a 0 to take the place of x to the 3. I have x to the 3, x to the 2, x to the 1, and x to the 0. Since I have them all, it doesn't skip any powers of x. I can just write out the coefficients exactly as they are. Okay. And then in the bottom, see, I have x plus 3. I'm dividing this whole thing by x plus 3. There's this form in, again, just for synthetic division. I'll say, well, what would I have to subtract from x for this to, it's like x minus a. And I'm going to take a and put it in a box right over here. Okay. So in this case, that would be -3. Right. So isn't this like x minus -3? Isn't that what x plus 3 is? Right. Or another way to say this is, what would x be to sum this to 0? Right. So maybe, okay, you guys get that? Okay. So let's run with this thing. Okay. Now I do have a coefficient of 1 on this x. My next example, that's going to change, and there's one more step you have to do. But for here, we'll just do a real straightforward example. Okay. All right, and then leave some space here and put a big old bar. Okay, now what we do, there's a process. We always take the first coefficient, you just drop it straight down. So that would be like a 3. Okay, so that didn't change. Okay. Then what I'm going to do is multiply this 3 by this -3 in this box and write that up here. So I'll say times this -3. Okay, but that process is going to complete. So I'll just go ahead and write this in times -3, something times -3. Right. We're going to repeat that step over and over. Because what is this 3 times this -3? -9. And now what you always do is you add these together. Because what is -2 plus -9? -11. Okay. Now I've got the next step set up already in pink ink. Because what is -11 times this -3?
-33.
It's positive 33. Okay. Because the negatives cancel, right? Negative, positive. And if I add those together, what is -53 plus 33?
-20.
You get 20. Aha. Okay. And then times this -3 again. Is what is -20 times -3? Yeah, positive 60. And then if I add that to the -60, that zeroes out. Now that's always a really nice result to get from synthetic division for it to end in 0. It doesn't always. If it ends in anything else, you have a remainder left over. Okay. In this case, it goes to 0. Right, so we have these coefficients left. Now, what do these coefficients apply to? I'm going to write down this 3. So it's like equals 3. Now, go back to the beginning. Guys, if you have x to the 3 divided by x, what does that leave you with? X to the power of what? 2. So it's 3x squared. This is minus 11x, and then minus 20. Okay. And this is exactly the answer. Okay. Just like that. All right, you guys get that? All right, guys good? All right. So I want to do one more synthetic division with you guys, and then I'll go back and do one more long division that has a remainder, and I'll show you guys how to work with that. Okay. And so here's a different synthetic division example. Example 5. Now this one, do you guys see right here? I'll write it out so it's bigger. We got 4x to the 4. Oh, there's no x to the 3 term. So you jump straight to 37x squared. I got a 4x and a 9. Okay, so we got that. And we're dividing this all by 2x minus 1. Okay. You guys see that coefficient of 2 on that x? We didn't have that before. Now, to use synthetic division, we do have to have a coefficient of 1 on the x, which we did last time, and it worked perfectly fine. So we have to make this a coefficient of 1. Guys, could I multiply this whole bottom by 1/2 to get a coefficient of 1 here? Could I do that? Multiply this by 1/2? Yeah, I could. But to restore balance, do I also have to multiply the entire numerator by 1/2? Yeah, you guys see I could do that, right? So I'm going to take everything, the top and the bottom, and say times 1/2 on top and times 1/2 on bottom, which I'm technically multiplying by 1. So I'm not really changing anything, just manipulating it. So I get a coefficient of 1 here. You guys see that? So I'm going to go, this is the same thing as 4x to the 4. Remember how there's no x to the 3 term? You guys see I'm missing an x to the 3 term? I'm going to write that as 0x to the 3. Okay? Right, that'll be important in the next step. Then minus 37x squared. Oh, whoops. What am I doing? I'm being silly. Scratch this. Okay, sorry. Okay. Guys, 4x to the 4 times 1/2. Oops. That's what I set this whole thing for. I got 2x to the 4. That's what I meant to do. Okay. I still have 0x to the 3. Okay. Now, 37 over 2. That's a funny fraction. That's okay. This is what I need. Okay. 4 over 2 is 2. x, and then I have this plus 9 halves at the end. I'm dividing that all by, and then this bottom binomial times a half is your x minus a half. Okay. Now this is in a form that's ready to use for synthetic division. All right, so you guys ready for the synthetic division? We're just going to take each of these coefficients one by one. So I got a 2, I got, well, a 0. You guys, it's really, really important. You do list the 0. You have to list the 0 because there's 0s to the 3 terms. Otherwise, it messes everything up. I got a negative 37 halves on the x squared. I got a 2 on the x, and I got a 9 halves constant. Okay? And I'm going to push through synthetic division. In this a term over here, guys, take a guess. I bet some of you guys figure this out. What am I going to put in this box? 1/2. Yeah, 1/2. Okay. Just like x minus a, or what would zero that out? They're good. Okay. Then put this bar here. And, okay, do you guys remember the first step I just did? Let's just drop down this 2. Okay. So I got a 2 here. Okay. And then I'm going to multiply that by what? Guys, what am I going to multiply that by? And this time it's 1/2, because I got 1/2 in this box. And that'll repeat here. So eventually something times a half, something times a half, something times a half. Right? Is that going to be true all the way down? Okay. So, guys, what's 2 times a half? Yeah, 1. And then 0 plus 1. What's 0 plus 1? 1. What's 1 times a half? 1/2. Okay. And then negative 37 halves plus 1/2 is that negative 36 halves, which I think is like negative 18, isn't it? What's half of negative 18? Negative 9. What's 2 plus negative 9?
Negative.
Negative 7. What's half of negative 7? Well, I guess negative 7 over 2, I could say that, right? And then what's 9 over 2 minus 7 over 2? So, yeah, 1, because it's 2 over 2, which is equal to 1, isn't it? Yeah, right. Now this time this process did not end in 0. Last time it did, so there was no remainder. Here, I'll show you guys. Here's the notes from a few minutes ago. It ended in 0. Okay. But this time it doesn't, so there is going to be a remainder. Okay, so what do we do this? All right, so remember my biggest power on x was x to the 4, and that was divided by x. So this is equal to 2x to the power of, power what? 3. Yeah, 3. Yeah. And then plus I have a 1x squared minus 18x minus 7. And then there's this remainder. So say, now guys, for this remainder right here, I'll label this remainder. Okay. How you actually finish that with a fraction is you put the remainder over the divisor, which is x minus half in this case. Okay? Is that okay? Okay. And that is a perfectly fine answer. Right? Or if you want to, guys, could I multiply this by 2 over 2? Say times 2 over 2. Okay. Just so that the divisor looks like it originally did, which was 2x minus 1. Okay. So this is the same thing as 2x to the 3 plus x squared minus 18x minus 7 plus 2 over 2x minus 1. Okay. So this is perfectly fine. This is perfectly fine. If Alex asks you, you can type in either one. It should give you full credit. Okay. Okay, guys good? Okay. All right, so that was a couple of examples of synthetic division that are a little bit different categorically. Okay. All right, I want to do one more example with you guys, which is this one right here, number 7 from the text, because I want to go back to long division, but also the one that has a remainder and show how to interpret that. So let's go back to long division. Long division. Let's do 2t squared, so they work with t instead of x, whatever, and different. Plus 13t plus 15. And we're dividing this all by t plus 6. So there's the setup. Number 7, straight from the book. So do a long division here. I'll set up this dividend as 2t squared plus 13t plus 15. I'm going to divide that by t plus 6. Okay. Hey guys, how many times does t go into 2t squared? Yeah, 2t. Yeah. So 2t. Okay. Then take this 2t multiplied by this whole binomial over here. So 2t times t is 2t squared. That was set up to cancel out. That's how you can do that. Then 2t times 6, don't forget that one. Isn't that plus 12t? Is that true? Right there. Okay. And then you subtract this off. Okay, synthetic division, we were always adding down. Long division, we're always subtracting. Okay. Plus, minus, minus. This goes away. And then, guys, what's 13t minus 12t? Yeah, just 1t. Yeah. And then drop down to 15. So say plus 15. Guys, how many times does t go into t? One time. So up here for the quotient, I'll do plus 1. Then 1 times t plus 6 is t plus 6. Then subtract this off. Reverse the signs. This goes away. Guess what's 15 minus 6? 9. Guys, notice this did not actually zero out. So this 9 is called the what? Starts with an R. Remainder. Remainder. Okay. So when you see this question in Alex, it says, what's the remainder? And you do process long division, you would, okay, the remainder is 9. Okay. If they want you to write out the rest of the fraction, guys, 2t plus 1 is not the full answer. It's 2t plus 1 plus 9 divided by the original t plus 6. Because weren't we originally dividing everything by t plus 6? Okay. This is the answer. I'll box this in pinky. Okay. That's the answer. That's the quotient right there. That's the answer. You see it? Okay. Now, I do want to show you guys what this looks like on a graph. So I did pop this one in Desmos ahead of time. Actually, I popped in the original expression. Got this, right? But now let's look at the answer, which is equivalent. Guys, isn't this question equal to this answer? The same thing? Okay. You can figure out what this looks like. Because what if there was no remainder? There's 2t plus 1. Isn't that just like a straight line with a y-intercept of 1 and a slope of 2? Isn't that what that would be? Okay. So this is almost that. Except it's never quite that because we're always adding on this little bit over here. And as this t gets really big, like 1,000 or a million or a billion, this last little bit approaches 0. So, so what that means is this. Right, you guys ready for this? I'm going to make a prediction here. I think that y equals 2t plus 1 is what's called the a slant asymptote. Okay? Wait, guys what I just wrote? Have you ever seen this phrase before? Did you guys learn this in Algebra 1, slant asymptote? You guys learn that? Okay, I'm seeing some yes and some no. I'll show you guys what that looks like on Desmos. Okay? But be prepared for that. This 2t plus 1, I'm treating this as 2x plus 1, basically, right? Okay. This boxed in answer is going to be very, very close to that straight line, but it'll never be exactly that straight line. Hence, it'll be asymptotically approaching this straight line, right? Which has a slope of 2 and a y-intercept of 1. Right? Also, guys, if you're dividing by t plus 6, what can t never be equal to?
-6.
-6. So t equals -6 is called the what asymptote? How about the vertical asymptote? Wouldn't that be true? Right, vertical asymptote? I think I need 2 asymptotes on this graph. A vertical line at t is -6, or x equals -6, same idea. And a slant asymptote, which follows this y equals mx plus b form. Okay? And the rest of the graph is going to sort of spread around those 2 asymptotes. You guys think? Okay. Now, in Desmos, I typed in the original expression up here, and I got this ready to go. So, let's see, where's Desmos right here? Right. Yeah, you guys see that expression that I typed in? I do want to show you guys that this expression that I typed in right here matches the original setup straight from the book. Okay? And the graph, I'm claiming is going to have these 2 asymptotes, one slant asymptote and one vertical asymptote. There they are. Yeah. See if I scroll back, you can see them. I have a vertical asymptote at x equals -6. I just changed t to x. It's the same idea. Right? And I have a slant asymptote that has a y-intercept at 1 and a slope of up 2 over 1. That's exactly it. That's exactly it. Of course, you could always make an XY table and plot a bunch of points, and eventually those separate curves will emerge right there. Get it? All right. So there's a rundown of dividing polynomials. Right. So quick recap here is if you're dividing by a monomial, you can very simply separate it into separate fractions and divide them all individually. If you're dividing by a binomial, you have a process of long division, or you can use synthetic division. If you have long division, well, either case, you might possibly end up with a remainder, which might indicate some kind of asymptotes that I showed you guys. Okay. And if you want to use synthetic division, and you're dividing by a binomial where the coefficient on x is anything other than 1, you do have to manipulate that first to get it at that coefficient equal to 1. Show you guys an example of that. All right, so a lot of fun examples here. So all these green highlighted ones I solved in the main video for you guys, including this word puzzle with these gardens going on right here. All right. So if you want to watch the full video with all those demos, you can. If you want to work on Alex, you can. I will walk around and help you guys out.